Hello, can you hear me?
I don't need to keep it in mind. Can you put good afternoon. So we will start the evening section, and the first speaker is Ashtekar, and he will talk about elevating tension in the CMB using Planck scale physics, and then a cosmic tango between the very large and very small. Please, you have 40 minutes and 5 minutes for discussion.
Okay, can you all hear me?
Yes, we hear you.
Okay, good. So, and can you see my screen?
Yes.
Share screen. Okay. So I guess I just have to go to full screen mode.
Full screen mode, please.
Okay, good. All right, so I'm going to summarize some work by many researchers, but in particular, the work that was done more recently with Brajesh Gupta, Dongwei Jiong, and V. Srinath. There was a PRL in 2020, and the details appeared in 2021. And this archive, this paper is in this archive, and that would be kind of the main reference for people who want to know more. So the past 3 decades have witnessed spectacular advances in our understanding of the early universe. We got observations which are to do with Cosmic Microwave Background Explorer, COBE, and then WMAP, Wilkinson Microwave Anisotropy Probe, and then Planck satellite. And Planck satellite has provided us the latest data coming from 2018. So in terms of theory, there is a precision measurements, and they are solidified and changed the direction of the program considerably, particularly starting from 1 part in 10 to the 5 CMB fluctuations, when the universe was only about 380 or 400,000 years old or young. We can arrive at the observed large-scale structure of the universe now, which is about 13.8 billion years later. It's a spectacular advance. In human terms, it is like taking the picture of a baby, and the baby is 1 day old, and being able to predict what it would look like when the person is 100 years old. So imagine how much biology, biophysics, and physiology you will need to know, and we know that for the universe in terms of physics and astrophysics. Quantum field theory plays a key role. This is a big realization, and this is a major shift from the 1980s. Cosmological perturbations in the early universe are represented by quantum fields on cosmological spacetimes in all systematic approaches, and they are not classical perturbations. And the origin of the tiny anisotropies seen in the CMB are traced back to the vacuum fluctuations of quantum fields. And so there is a really brand new cosmogenesis that the origin of the large-scale structure lies in quantum vacuum or quantum nothingness. So the picture here schematically is basically that we know this what is happening in the when the universe was about 380,000 years old, and then with the theoretical predictions we can get the large scale structure of the universe. And as I just said, in human terms, it is like taking a snapshot of a baby 1 day after the birth and providing the accurate profile at age 100. So currently the most commonly used paradigm for the early universe comes from inflation. One can forego initial motivations and focus more on the observational and successes and conceptual limitations. One can recall, for example, Dirac's motivation for the famous Dirac equation was completely incorrect. But on the other hand, the equation has been extremely useful. And the idea is that the same thing will be true about inflation. From space-time perspective, there is a limitation, namely the paradigm continues to use general relativity with its Big Bang singularity. And it just begins, so to say, in the middle when space-time curvature is about 10 to the minus 11 Planck scale, and we need quantum gravity to go beyond. The viewpoint is that one shouldn't regard inflation as a fundamental theory, but rather as a framework to hang the fundamental theory. And this is a viewpoint that was advocated by Jim Peebles, and that is a viewpoint we're adopting. To arrive at a fundamental theory, note that neither CMB nor the success of inflation implies that there was a Big Bang. Big Bang is a prediction of general relativity in a domain where it is not applicable. Indeed, as Einstein himself said in 1945, one may not assume the validity of field equations, that is to say Einstein's equations, at the very high density of field and matter, and one may not assume, and one may not conclude that the beginning of the universe should be a singularity in the mathematical sense. Indeed, by now, cosmologists mean an early hot phase in the universe and not an initial singularity. And there is a nice video, which is very short, so beginning researchers will really profit from it, in which 7 of us were interviewed, including Stephen Hawking and Roger Penrose. And we sort of were interviewed separately. We did not know what the other people were saying. And it's only when the video came together that we heard each other. And we all say the same thing, that in fact, Big Bang is not really the beginning of the universe. It is an early hot phase of the universe. And this viewpoint was really advocated about 15 years ago, or 15 to 20 years ago, very strongly in loop quantum gravity, and that the Big Bang is really replaced by Big Bounce, as we will see in a minute. So this really is the rest of the talk I would like to divide as follows. First, I would like to tell you that what the 6 parameter standard cosmological model is. Then we'll go beyond inflation and talk about loop quantum cosmology. And then I'll tell you the results, which have to do with alleviating the CMB. And there is a very interesting cosmic dance between the very large and the very small. So basically, recent advances have opened an unforeseen window to go beyond quantum field theory in cosmological spacetimes and use quantum gravity proper to go beyond the Big Bang. This is a fascinating interplay between detailed calculations based on the quantum nature of geometry in loop quantum gravity and the CMB observations of the Planck collaboration. And as I said, there is a short account in the Physical Review letter last year, and more details are in this year's paper. So let's just begin with how the 6 parameter cosmological model is actually arrived at. Motivated by inflation, one assumes that the primordial power spectrum of cosmological density or temperature fluctuations are nearly scale invariant, and therefore one makes a standard ansatz, which is the power in the scalar mode, curvature perturbation, is really given by the 2 parameters: the amplitude, the scalar mode, the scalar perturbation, and a spectral index. So K by K star is really, K star is a fiducial the wave number, and K is the actually observed wave number. If NS was equal to 1, this factor would go away and the power would be exactly scale invariant. So the departure from 1 is what tells us that it is not exactly scale invariant. In fact, the power spectrum, as is well known, has a red tilt. There is slightly more power towards the red part of the spectrum, smaller wavelength, smaller wavelength than towards in the higher wavelength modes. So towards the red part of the spectrum, that is just smaller wave numbers than in the higher wave numbers. To evolve these primordial perturbations using astrophysics, one needs to specify 4 other parameters. And these 4 other parameters are the matter densities in baryons and in the cosmological constant, if you like, and then or dark energy sometimes as it's called. And we have to really also say what the 2 other parameters, namely the angular scale, the baryonic oscillations, which is called 100 theta MC, 100 times the angle subtended by megaclusters, and the reionization depth. So these are really featuring in the late universe, and the point is that they dictate the propagation of the CMB photons to us, all the way to us. So therefore, we got 6 parameters, 2 primordial and 4 in the later time universe. And then the statement is that using astrophysics, we can determine, starting from the primordial spectrum, some spectra that we should be able to observe, and which have to do with the TT, temperature, electric polarization, and lensing amplitude. So these are the correlations. To begin with, they are really functions of theta, but where one does spherical harmonic decompositions, and one gets the CLs here. Nothing depends on M just because of the symmetries of the problem, and everything just depends on L's up here. The 4 correlation functions up here can be measured observationally. And so if we compare the theoretical predictions with observations, then you get a probability distribution for the 6 parameters that we just saw. And the mean values of the marginalized probability distributions provide us with the values of the 6 parameters. And that is a 6-parameter universe according to Planck. And because we got probability distributions, we also get 1 sigma spreads. And this is what is reported in all the Planck papers. So the lambda CDA model selected by Planck has had tremendous success in explaining all the major features in the temperature and isotropics and polarizations of the cosmological microwave. And this is something that we have seen again and again. You see up here at large scales or small wavelengths that in fact there is an excellent agreement between theory and observations. And this is really non-trivial because observational errors here are really very small. For the small K, larger wavelength, observational errors are larger. But again, still, there is a good agreement between theory and observations. And furthermore, once this 6-parameter map model is determined with this fitting with the 4 correlation functions, then one can predict not only one can predict the precise spectra, but one can also then have new predictions which are to do with the odd parity, BB per power spectrum, and the lensing amplitude. But however, this is, although all this was a spectacular success, CMB data also exhibits certain anomalies that bring out the tension between the best fit lambda CDM model and observations. And I will focus on 2 of them. There's a large scale power anomaly. If you go back, you see here that in fact, much of the power is actually observed power is lower than what is predicted by the theory. But this is not so vivid, so clear in that particular picture where we have done the spherical harmonic decomposition. What I'm plotting is the CLs, and these are Ls up here. What I can do is go back and go to the correlation function, which depends on angle, C theta, and then see what happens to those C thetas, and directly in the angular ones. So here I'm plotting theta and here C theta. And you can see that the observations appear in the blank again. And you can see here that C theta is really very, very small. There's very small power here after about 60 degrees in sky. This dip up here should not be taken too seriously because it has to do with the masking errors that come in order to remove contamination from our own galaxy at about 180 degrees. So over here, there's really a power separation, very little power, whereas the standard cosmological model based on the standard answers is really saying that this is the power subspectrum. And there is really, there is a measure which is called S1/2 that was proposed by various cosmologists, which is basically taking C of theta whole squared and then integrating it on all angles. It doesn't depend on phi. So integrating on the sphere is the same as integrating on d cos theta or sine theta d theta. And this measure, we can calculate this S1/2 both for theory and experiment. And one finds that the theoretical prediction is something like 35 times larger than what is actually measured. The second is a lensing amplitude anomaly. What is lensing amplitude? Well, as a CMB travels from the CMB surface, the photons travel from the CMB surface about 380,000 years after the beginning of the universe, then one finds that they undergo certain lensing due to various gravitational distribution of matter. So there is a gravitational lensing that is occurring up here. And what one finds is that in the 6-parameter family model, lensing amplitude is assumed to be 1. But if you actually allow it to vary, then it assumes a value which is slightly bigger than 1. And this value is really outside the 1 sigma contour observationally. So basically, the theoretical value that is assumed is here, is here, and the 1 sigma contour between in this plot between the lensing amplitude and this the optical depth is really the dark red, and you see that it is outside the value. Why are we plotting it against optical depth? Because optical depth is the least well measured parameter of the 6-parameter values that we talked about before, and that is why it is more useful to look at this particular plot up here. So AL equal to 1 lies outside 1 sigma level, and that led to a recent suggestion 2 years ago by this gentleman saying that there is a possible crisis in cosmology because there is an inconsistency. Cosmological model assumes AL equal to 1, and this value that is assumed lies outside the 68% confidence level. So now, should we be concerned about this cosmological this anomalies that one is actually seeing in CMB? Well, the statistical significance of any one anomaly is quite low. It is only a 2 to 3 sigma. So, if you do realizations of the theoretical models, then you will see that the observed cosmological model is actually going to appear in about once in 1,000 realizations, and that is considered okay. That is not serious problem. But if you take 2 or more together, then we really live in a very special realization, 1 in a million, of the posterior distribution function predicted by the theory. And therefore, any time you can resolve 2 of these anomalies by some new effect, would be considered as a very significant progress. And in fact, that is what the Planck team says. If any anomalies have primordial origin, then their large-scale nature would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring any models that might explain an anomaly, or even better, multiple anomalies, naturally with very few parameters. And that is what many people in loop quantum gravity have been doing, trying to see if, in fact, we can do that. After all, the early universe is a nice window for quantum gravity effects. In fact, the only really observational window available today. And so, are these anomalies somehow related to quantum gravity? Now, the standard assumption is really, which is called the standard answers, SA, is really this thing that this formula that I wrote before, that the primordial aspect. This is not the observed one, but the primordial one, which is, for example, at the end of inflation, is nearly scaling that. Now, Suppose, surprising as it may seem, the standard answer is actually modified by the quantum gravity considerations. In the loop quantum cosmology, the primordial spectrum is nearly scale invariant, follows this pattern, but really for large K. For small k means larger wavelengths and therefore larger angular scales appear. So small, if you like, that larger angular scales bigger than 60 degrees that we saw before, or if you like, in terms of YLMs, L less than equal to about 30. At those small scales, there is actually power suppression already in the primordial spectrum. And therefore, one would hope that when you propagate this primordial spectrum CMB using astrophysics, then in fact, one would actually get some power suppression at the large angular scales at low K. And this possibility that was raised by Planck is indeed realized in loop quantum cosmology, and this is a manifestation of quantum gravity in the sky. So this is the first part that I've done. Now I'll tell you about loop quantum cosmology, going beyond inflation. So basically, what do we need to go beyond inflation? Well, in loop quantum cosmology is a cosmological sector of loop quantum gravity. As we will see, there is excellent agreement with inflation at small angular scales, but departures at large angular scales, where the CMB anomalies lie. So I would like to make this detour about basic ideas of loop quantum gravity. So first, let us recall that general relativity is founded on Einstein's outrageous idea that gravity is not a force, but a manifestation of curved nature of space-time, curved geometry of space-time. Therefore, general relativity needed a new syntax to describe classical physics in presence of gravity. And that new syntax, this new mathematics, was Riemannian geometry. In loop quantum gravity, the viewpoint is that geometry is like matter because it is a physical entity that can be acted upon and acts back. And therefore, it also has atomic structure, just like matter. And therefore, quantum gravity needs also a new syntax to formulate known physics. And this would be quantum Riemannian geometry. Just as in atomic physics, we need quantum mechanics to describe quantum geometry, to describe the geometry at small scales, we also need quantum Riemannian geometry. And this was systematically developed by a large number of researchers over the last 3 decades. And then the basic ideas are the following for quantum geometry. The geometrical operators, such as area of physical surfaces and volume of physical regions, are quantized in a precise sense, and the eigenvalues are discrete. And the continuum picture arises only as a coarse-grained approximation, like an impressionist painting that we're seeing here. At fine grains, we don't just have dots. We have some atomic structure, if you like. But when you look at it from far away, it looks like a nice continuum picture that has emerged. The discrete eigenvalues of area operator and volume operator, they crowd exponentially as they grow, making the continuum of general relativity excellent approximation very quickly. But the fundamental discreteness of quantum geometry, in particular the smallest non-zero eigenvalue of area, and that is called the area gap, that plays a crucial role at the Planck scale physics. Cosmological models have the nice feature in loop quantum cosmology that all curvature singularities are naturally resolved. And physical quantities such as density, curvature, and isotropies that diverge at the Big Bang remain finite and furthermore have an absolute bound on all physical states. There's an interactive video on loop quantum gravity, 70-minute long. It is done very nicely professionally, so you might want to see it to know more about loop quantum gravity. And just earlier this year, the reviews of Progress in Physics commissioned a review article, and that has already appeared in the journal, but in the archives, you will see it here. It's a short article for non-experts, so you might be able to, research students might be able to profit from it. Okay, so the question now we want to ask is that in loop quantum gravity, I just said that singularity is resolved. What is behind this singularity resolution. How did this have come about? Well, one does not assume any unphysical matter or new boundary conditions like Hawking boundary conditions. Rather, quantum geometry creates a brand new repulsive force in the Planck regime, and that overwhelms the classical attraction. The Big Bang is replaced by Big Bounce. And this has been analyzed in detail in the Hamiltonian, path integral, and consistent histories framework by many, many, many people that has been that are listed, some of whom are listed here. In FLRW models, the quantum Einstein equations dictate the relational evolution of the wave function of the background Friedman model on which the wave function of perturbations actually evolve. For this background model, observations like matter density and curvature, they remain bounded on all solutions. But there is a universal upper bound, and those are determined by the area gap. For example, the maximum energy density is given by 1 upon the area gap Q. There are many generalizations of this. There are thousands of papers, including the cosmological constant, inflationary potential, anisotropy, simplest inhomogeneities, etc. So this picture is quite robust. Here is an example of the Starobinsky potential, and what we see is the following. What we're plotting up here on the x-axis is the volume of some fixed region of the physical volume of some fixed region in the universe, and then on the x-axis, and the y-axis is the infraton. And as the infraton rolls down the potential, the universe expands exponentially, and this is the inflationary phase. But if you go back in time, the inflaton has a turnaround, and in classical general relativity, the volume would go to 0, and then that is a Big Bang singularity. But in loop quantum gravity, there is a effective repulsive force that comes up due to quantum geometry, and that causes a bounce, and therefore the volume doesn't go to 0, but rather the universe starts expanding again in the past. And the same thing is true for other potentials. I'm just skipping over the details up here. And now one might ask, why does this matter? Well, it matters for the following reason. In general relativity, if you look at the radius of curvature of the universe, then what one finds is that the scalar curvature blows up, and therefore the radius of curvature goes to 0. So the radius of curvature has this contour in classical general relativity. And what I'm plotting here is length scales and time. These are typical modes we see in the CMB. And they really remain inside the radius of curvature. And therefore, they don't feel the curvature. It's like you walking on the surface of Earth. Your wavelength, your footstep, is much smaller than the radius of curvature of Earth. Therefore, you don't feel the curvature. But if you take a plane and fly, then you'll actually feel the curvature of Earth because the wavelength is larger. In loop quantum cosmology, because the curvature does not diverge at infinity, the radius of curvature is not 0, but it's finite. And therefore, there are modes which are actually outside the radius of curvature. These are longest wavelength modes. They experience the curvature during the Planck epoch. They get excited, and therefore, they are not in the standard Bunch-Davies vacuum. And therefore, there are completely new effects associated with them. And these are the longest wavelength modes. Thus, there's a very interesting unforeseen interplay between the ultraviolet and the infrared. The curvature singularity is removed because of the infrared. Oops. Sorry about that. The curvature singularity is removed because of the ultraviolet, but that actually has effect on the longest wavelength modes, and that is the infrared point that I was just mentioning. So now let me just talk about the results and the summary. So the results are the following. If you look at the primordial power spectrum of the scalar modes, and if you take the LQC prediction and divide by the standard ansatz, so standard, if I had put standard ansatz here, I should get to 1. And you see that they agree very much for large K or small wavelengths, but at larger wavelengths, in fact, there is a big departure up here, as you see, and there is a power suppression in LQC relative to the standard ansatz. Then if you now that was the primordial spectrum. If you evolve it using the standard course of CMB, you find, of course, complete agreement at large K, but at small k, relative to the standard ansatz, which is in red, the power is suppressed, and therefore there is better agreement with the observations. And this we can see explicitly in the C theta plot. The C theta plot that I told you is a better measure of the power suppression. Namely, there is power suppression after 60 degrees. And you see here that this was the experimental value. This is really the prediction of the standard ansatz of inflation. And this is the LQC prediction up here. So there is an improvement. There is actually the anomaly is reduced by a factor of 2/3. So there is a 2/3 reduction in the anomaly up here. And the same thing is true with the anomaly of the lensing amplitude, the AL tau plane that we saw before. So here is a lensing amplitude, here is an optical depth. In blue up here is the LQC prediction, and in red is the standard ansatz prediction. So standard ansatz, one sigma contour was this, and the value AL equal to 1 was outside that. Whereas in LQC, the 1 sigma contour is this, is blue, okay? And this is in the 1 sigma contour. So therefore, the statement is that it is really within the standard deviation. All the results of Planck are actually given within standard deviation, 68% probability, and therefore there is no tension in LQC. The tension is completely elevated, and there is no reason to bring in spatial curvature, and there is no possible crisis in cosmology. So these two anomalies are actually naturally elevated. And furthermore, you can now go back and see what are the parameters, the 6 parameters that we talked about, what happens to them. And what one finds is that for the 5 of them, in fact, the values that the standard ansatz predicts, standard inflation predicts, and LQC predicts are very, very close to each other. But for the 6th one, which is optical depth, there is almost a 10% difference up here, and or 9.8% difference. And similarly for this S1/2 that I told you before. But these are the parameters that determine the universe we live in. So according to loop quantum cosmology, we live in a somewhat different universe than the standard ansatz, and the future measurement missions of tau, optical depth, as well as there are differences in predictions for the BB, the OR parity polarization measurements that are going to be made, and that will distinguish the standard ansatz from the LQC predictions. And so that is exciting. So let me just conclude. Let us recall the quote from the Planck collaboration from the 2018 results. 2018 results. They say that if any anomalies have primordial origin, then their large-scale nature would suggest an explanation. Can you hear me? Yes. Okay.
Yes, we hear you.
Okay. So if any anomalies have primordial origin, then their large-scale nature would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring any models that might explain anomaly, even better, multiple anomalies, naturally or with just a few parameters. And what we're seeing is that and it goes on to sort of say why this is interesting. And what we saw is that LQC provides a concrete illustration of the desired primordial mechanism to significantly alleviate 2 anomalies. And the interesting thing is that these anomalies are alleviated without really affecting the successes, the really big successes of the standard ansatz standard model at large K or small wavelengths. So there we got lots of measurements. It could easily happen that loop quantum cosmology, because of the Planck scale effects, might have changed those predictions, and that does not happen. So we keep all the successes and we alleviate 2 anomalies in loop quantum cosmology. And then there is a 9.8% higher reionization optical depth, tau, and that will be measured accurately using completely independent methods, for example, using fast radio bursts. So radio waves, not CMB at all. And so one would be able to confront CMB predictions, which are either with the standard answers or with loop quantum cosmology and observations. And then there is a different spectrum for the odd parity at large angular scale that could be measured also by the beam mode mission. And the work is also progress on other anomalies by other authors, which I think is very exciting. And that uses work based on non-Gaussianity and so on. So the important thing that I want to say is just really the following, that for the longest time, quantum gravity talks that we heard and so on, that I myself have given, really depended on mathematical structures, conceptual problems, rather than observations. There is almost no contact with observations. To me, the most satisfactory part of this development is that we really have close contact with observations, and quantum gravity has descended from its lofty heights of mathematics and conceptual abstraction to concrete applications. Now, it could be that these predictions are based on certain assumptions, and it could be that those assumptions are wrong and they would be revised, but that is how progress occurs in other forces of nature. That is why, for example, we are guided by the large colliders, the large hadron colliders at CERN, and so on. And so this, to me, is the most satisfactory part. Quantum gravity is really coming in its experimental phase. Thank you.
Thank you very much. So, question from the auditory? Yes, please.
Hello, can you hear me?
Yeah.
Okay, so you said that in this model, the Big Bang is replaced with a big bounce.
Right.
The question is, what happens to the entropy? Was it decreasing before the big bounce, or what happened to it?
Yeah, so depends. The entropy, we have to be careful about adding also gravitational entropy. And so there are certain horizons in the past bounce. We have to take into account that entropy as well. And then what one finds is that, in fact, the cosmological horizons, if you take the entropy of the matter and the entropy of the cosmological horizons, the total entropy is actually increasing.
More questions? Go ahead.
Hi, Abhay. Just a quick question. So the result that you shown for the curve of the power spectrum is independent of the value, the specific value of the Barberi-Mirzi parameter?
Oh no, that's a good question. No, it is not actually. It depends on the value of the. I would like to, if you don't mind, I don't like to think in terms of Barberi-Mirzi parameter, but it's equivalent. But I would rather talk in terms of the area gap. So it depends on the value of the Barberi-Mirzi parameter or the area gap, and where you use the standard value that is normally used in cosmology. So what we can do is we can vary the Barberi-Mirzi parameter or the area gap, and we can see, well, the value that is actually used is area gap, which is about 5.17. Is that area gap within the 68% confidence level? And the answer to that is yes. Actually, the paper I gave you, the preprint, the preprint number I gave you, the paper has already appeared. That will actually give you a good, a better plot than what I'm showing up here. That will show that the area gap that is assumed is actually within 68% confidence level of the CMB prediction. Now, this is to me very, very surprising. I mean, very nice and very nice confirmation, because an increase in the area gap by a factor of about 10 is observationally ruled out, and the decrease by a factor of 10 is actually ruled out at 68% confidence level. So this 95% confidence level, this 68% confidence level. So that is to say that we are on the right track up here. Now, this is especially exciting because of the following reason, that the area gap or the Barberi-Mirzi parameter was really first obtained using the arguments having to do with black hole entropy. Had nothing to do with cosmological space-time. So the value that is coming from the black hole entropy calculations is completely within the 68% level of the value, 68% level of the measured value, if you like. I mean, what we have done up here is exactly what was done for the optical, for the lensing amplitude, namely, in what people had done was to say that lensing amplitude is set equal to 1. So after everything is done, we say that people say that, well, let us vary it and see what happens. And in the standard answers, the value 1 is outside the 68% confidence level, whereas in LQC, it is within 68% value. So here is a similar thought experiment. Namely, one says that, well, we assumed a certain value of Barberi-Mirji parameter to draw all the plot, to show all the plots that I showed before, like these plots up here. Now let me say that, let me vary, let me allow it to vary, let me allow it to float, the Barberi-Mirji parameter or the area gap, and then see what happens. And what is nice is, if it had not been a 68% confidence level, then one would say there's a tension, but there is no such tension. So there is coming together completely different areas, and that is rather exciting.
Thank you very much. So let's upload to the speaker. Thank you very much. So we will move to the next speaker. Professor Ross. He will talk about R-square Higgs inflation, gravitational contact terms, and the hierarchy problem. So you have 40 minutes and 5 minutes for the questions. So please follow the time. Thank you. We did not hear you.
Can you hear me now?
Yes, now.
Okay. And can you see my screen?
Yes, we see your screen.
Okay. Well, thank you very much for the invitation to talk at Corfu, if only virtually. I'm a frequent visitor, and this virtual visit is one of my first. I hope it may be the last, and I can appear in person in future years. So what I'd like to talk about today is R-squared Higgs inflation, and really the question of whether it has a hierarchy problem. The work I'm talking about is largely done with Pedro Ferreira, Chris Hill, Johannes Noller. So let me start with an introduction to R-squared Higgs inflation. Here we go. Starobinsky around 1980 proposed adding to the action an R-squared term, where R is the Ricci scalar, and this, together with the Einstein-Hilbert action he showed, could give you a period of inflation. And the inflation that one got from the Starobinsky model is still consistent with observations. Sometime later, Bezrikov and Shapozhnikov, Cervantes, Kuta, and Danon explored the possibility of getting inflation by a different method, which is to add a non-minimal coupling of the Higgs field, which I've called H here, to the Ricci scalar. Now, it turns out these models are related in a very intimate way, and their predictions are essentially the same. In these models, where you combine the Higgs field and its non-minimal coupling with an addition of an R-squared term, the slow roll is governed by an effective single field model with a modified sound speed, and we'll see that as we continue. And the predictions of the model are right central to the observations, as Lindy discussed in some detail yesterday. Now, over here, I've listed just three papers that I found particularly useful. It's impossible to list them all because I counted over 500 papers dealing with R-squared Higgs inflation. One of the reasons is it's such an elegant model based almost entirely on what we know already, and is adjusted by a single parameter, so it's very predictive. Now, the R-squared Higgs action is originally defined in what's known as a Jordan frame, in which the Einstein-Hilbert action plus kinetic terms for the Higgs and a potential for the Higgs, written in blue, are added to this, are the R-squared term of Starobinsky and the H-squared R term of Higgs inflation. In many ways, the R-squared term is useful to Higgs inflation as it allows you to control the non-perturbative aspects of the theory, and it can be perturbative up to the Planck scale. Also, it's been argued that the radiative corrections, particularly due to the anomalous Higgs term, will actually generate such an R-squared term, so you shouldn't perhaps ignore it. Well, the form that I've got to start with, the R-squared term, is usually rewritten using an auxiliary field in terms of an anomalous coupling of the auxiliary field phi to the Ricci scalar in a similar manner to the way that Higgs inflation couples the Higgs to the Ricci scalar. If you take this form and apply the equations of motion, you get an equation that's solving for phi, substituted back in there, immediately gives the R-squared term. So in that sense, you've just rewritten the R-squared term in this form. Given that we have these two anomalous couplings of scalars to the Ricci scalar, you might ask, what's the physical implication of these terms? So let me turn to that. And what I'll argue is this is clearly seen in the effective Lagrangian via so-called contact terms. Contact terms are terms that arise through the exchange of a massless particle with a propagator going like 1 over q squared, where the 1 over q squared is actually cancelled because in the numerator, one has a coupling which is proportional to q squared. So the q squareds cancel out. This, in this case, 4-point amplitude becomes a point-like effective operator from otherwise a single particle reducible graph, and should be included, necessarily included in the effective Lagrangian. This is actually quite well known in QCD. The so-called penguin graphs in QCD are contact interactions because they're driven by a gluon exchange with a massless propagator, 1 over q squared. And in the numerator, there's a q squared factor coming from a coupling, which I've shown here, of the d quark to the s quark via W boson, giving you an additional q squared term when you expand out the derivative acting on g mu nu. And so at the very end, you get a 4-fermion operator, point-like, that needs to be included in the Lagrangian is actually necessary to explain hadronic weak interactions. The same thing happens with gravitational interactions, giving you gravitational contact terms. And this can be simply seen by doing a calculation in the weak field limit, expanding about flat space. So we have the Minkowski metric and h mu nu being the perturbation about that. If you take this, then the Ricci scalar can be written in terms of pi mu nu h mu nu, where pi mu nu is written as shown here. And I find it convenient then to separate terms in the action, something I've called S2, which comes from substituting R into the first term, and into the second term rather, and gives you a coupling between alpha phi squared and h mu nu of the form written here. H mu nu also couples to the energy momentum tensor, and I've called that coupling S3. So how does the contact term work? Well, you take your vertices. In this case, I've taken two S2 vertices, where S2 is written again here. And I put in the graviton propagator with the 1/q² singularity. And so working out the product of the two S2 terms trapped between the propagator polarization, you end up with these pairs of derivatives squared, one of which becomes a q² and cancels the 1/q², leaving a point-like operator of higher dimension, what I've called S2, S2. Well, you can do exactly the same thing, coupling S2 and S3. And when you go through the same motions of computing the vertex times the propagator, you find again, you get a q² factor coming from the derivative squared term that can cancel the 1/q². Putting all of that together gives you a higher dimension operator, phi to the 6 divided by the Planck scale, S2, S3. So these are contact terms that are inevitably present. Now, the normal way of dealing with these anomalous couplings of scalars to the richer scalar is by an Einstein, a Weyl transformation, taking you to the Einstein frame. So starting again in the Jordan frame with the Einstein-Hilbert term and this anomalous coupling, putting those two couplings together times R, one then does a Weyl transformation, rescaling the metric by this factor omega to the -2, where omega squared is given in brackets up here. So the fields transform according to their dimension. The scalar fields will also have a transformation under this Weyl transformation. And also R will transform in the manner shown. So then it's a relatively straightforward procedure to substitute omega into this equation and taking account of the change in the metric, one finds that the so-called Einstein form of the action is given by the normal Einstein-Hilbert action plus additional terms. And in what I did with the contact terms, I expanded to order 1/mp², so I'm going to do the same here. And when I do that, I find terms that are identical to the contact terms. The S2, S2 term is the first one. The S2, S3 term, the phi to the 6 term is the second one. And then there are further terms of order 1/mp⁴ that I'm not exhibiting here. So what does this mean? Well, this actually means that the Jordan frame, including the necessarily present contact terms, is already the Einstein frame. If you try and calculate in the Jordan frame without taking account of the contact terms, you will get answers that differ from the answer you got by Weyl transforming to the Einstein frame. But once you realize what the contact terms are doing, you realize that these two frames, although called differently, are actually essentially the same. So that's by way of an introduction to solving this type of equation. So let me now go back to the R² Higgs action that I gave some time ago. Here, the first term is this R² term rewritten in terms of the auxiliary field, and we've also got the anomalous H²R term. So I grouped the terms proportional to R together with this factor omega squared, and omega squared in this case is 1 minus alpha h of a 6mp² h² minus alpha 5 of 6mp² phi². But as we'll see, it's important to change variables and define this combination in terms of a new field chi. This chi field will turn out to be the field driving inflation. So let's see how that goes. You take this action and you include the contact terms to eliminate the anomalous terms. It's equivalent to doing the Weyl transformation as I discussed before. And you end up with the Einstein-Hilbert action plus derivatives of the chi field. And this chi field is known as a scalaron. associated with the original R² piece of Starobinsky. Then we look at the potential that came about involving the auxiliary field, the phi to the fourth term. It gets scaled by omega to the -4 in this change, including contact terms. And in fact, this term plays the role with the inflation potential, as we'll see in a moment. Phi squared, you can solve from the condition that 1 minus terms proportional to a squared and phi squared is related to chi to get this result. So I substitute phi squared in here, and knowing omega squared from this formula, you construct the R² Higgs inflation potential. And it is a relatively simple form that I'm sure you'll recognize, at least the first part, as being the Starobinsky potential. It's got an included effect due to the Higgs. The properties of this potential are such that for suitably large initial conditions of the fields, you're in an initial attractor valley. And that valley plays the role of connecting the vev of chi to the vev of h. And so instead of independently depending on chi and h in the valley, it depends only on one effective variable. And this effective variable has a mass. We call it the effective scalaron mass. And that applies while you're rolling in this valley. So it's during inflation. And the effective scalaron mass is given in terms of the scalaron mass and a factor in here that also involves the anomalous coupling. So both the Higgs and R² inflation are described by this. If you track it, you can see that the Higgs inflation applies to the largest values of alpha h that are possible while still being perturbative. If I had larger values of alpha h, it would become non-perturbative and one would not be able to compute the predictions of the theory. Smaller values of alpha h give you terms that are essentially R² inflation and dominated by the first piece. So what about the physics of this? Well, it's a one parameter model in the sense that this effective scalaron mass determines the amplitude of the primordial curvature fluctuations and fixes this effective mass to be around 10 to the -5 Planck masses. In terms of F0, m chi is related to F0 with a relatively factor of order 1, so F0 is also of order 10 to the -5. Here, I've just written that out explicitly. M chi is of order F0 times m Planck, which gives me 10 to the -5 times m Planck, which is of order 10 to the 13 GeV. So the model R² Higgs inflation has a scalaron whose mass is can be slightly greater than 10 to the 13, but in all cases is of that general order. And this by itself should raise some alarm bells because it suggests there might be some hierarchy problem associated with the Higgs. The Higgs, as we see up here, couples to the scalaron. And if we have a coupling between the Higgs and a heavy particle, you can generate large radiative corrections to the Higgs mass. Well, you might argue these are absent at a high scale if you have some underlying scale invariance, but they'll be recreated by radiative corrections. And that's something that I'm going to discuss in a moment. Of course, this hierarchy problem is dwarfed by the hierarchy problem of the cosmological constant that we heard more about in previous talks. My own point of view is that the cosmological constant is strongly IR sensitive. For example, Woodard and Samus would suggest that the gravitational radiative corrections become non-perturbative and non-calculable as you go towards the far infrared where the cosmological constant is measured. We heard another suggestion from Diwali yesterday that as you roll towards the infrared, you go towards the unique vacuum, which has zero cosmological constant. And there are other suggestions. So from my point of view, it makes sense to discuss the hierarchy problem of the Higgs without having to solve the cosmological constant problem beforehand. So let's discuss that in some more detail. Scale invariance and M Higgs. By that I mean, suppose at in your ultraviolet theory, you have an underlying scale invariance that forces the Higgs mass to vanish. How will radiative corrections affect this? Well, if the Higgs couples to a massive particle that with mass mx, the beta function that you have for the renormalization group running of the Higgs mass is proportional to mx squared. And so when you calculate the radiative corrections at some cutoff scale lambda, it is given by mx squared log of q squared plus mx squared, where q squared is the momentum flowing through the Higgs. Now, suppose this is scale invariant at a high scale lambda, which means I'm going to set m squared at q squared equals lambda to be 0. I do this by setting the bare value of the mass to cancel delta m squared. And this can be natural if due to the scale invariance. But you can see from the general form that this doesn't imply that the mass of the Higgs at a low scale, at the electroweak scale, for example, should remain 0 because of the logarithmically varying terms that gets cut off at the scale of mx, but has a coefficient mx squared. So as you come down from the original Planck scale, will generate terms. And this is what I would refer to as a real hierarchy problem, the existence of these logarithmically varying terms contributing to the Higgs mass. Well, in the standard model, mx is confined to electroweak mass states, such as the top mass, Wz, and Higgs mass. And these clearly, being proportional to this mass, will generate at most electroweak scale corrections to the Higgs mass, which doesn't correspond to the usual definition of fine-tuning when everything is of the same order. And this is what Bardeen meant when he said the standard model was natural. Well, what about the R-squared Higgs model? Now, of course, mx contains states which are very heavy, namely the scalaron state of around 10 to the 13 GeV. The question as to whether it generates a hierarchy problem then becomes one of what the couplings are of the Higgs to the scalaron. And that is something one can turn to and calculate. So the calculation of Higgs mass correction can be done in various ways. Originally, what we did was we constructed from the interactions that you read off from the R-squared Higgs potential between the Higgs and the scalaron, and just do a Coleman-Weinberg effective potential calculation. Here, I'm just going to present a slightly different method, which is using renormalization group equations. It ends up giving you the same answer, and in many ways is sort of more elegant, so it's useful to present it this way. So the generic structure that we start with is a potential for the scalaron and the Higgs, kinetic terms for those, and we can expand this potential up to dimension 4 terms with coefficients written here, several of them. Each of these coefficients has a renormalization group equation involving all of the coefficients and is easy to calculate. Indeed, I'm showing it here. The RG equations for the various coefficients are listed here and are well known. So what can one do then to use this to calculate the effect on the Higgs mass of the R-squared Higgs initial conditions? Well, the way to do that is to set these parameters at the Planck scale equal to that found in the R-squared Higgs potential, and imposing a scale invariance that would make the masses vanish at that scale. So I'm going to do that now. I have the expansion of the scalar and Higgs potential at order, up to order, quartic order, and I compare it to the coefficients that I have in my general potential, and that determines, for example, the Higgs mass is initially 0 because of scale invariance. The others are generated in the appropriate form from this, comparing these two equations. And then you just plug these into the renormalization group equations for the beta function of mh squared, and use that to get the radiative correction to the Higgs mass, which is given in this form here. So this would be the Higgs mass evaluated at the Higgs mass scale or electroweak scale. It's given in terms of the proportionality to the scalaron mass, which is this term here, written in terms of the Planck mass and F0. It has the couplings, and the couplings in this instance involve the anomalous couplings of the Higgs to the Ricci scalar. They can be read off from the contact terms. And we have a log which is cut off at the scalaron mass, starting with the boundary condition, which I set at the Planck mass. And this I can now use to quantify whether or not I have a hierarchy problem in the model. So the fine-tuning measure looks at the magnitude of delta mh squared compared to the physical value of mh squared. I had this formula on the previous transparency, and I just plug in the values. F0 is essentially 10 to the minus 5, whether it's Higgs inflation or Starobinsky inflation. It's cut off at the scale m chi squared, which is 10 to the 13. And alpha h, well, alpha h in Higgs inflation is known. It is large, and that effectively is what's driving the inflation. It's around 3 times 10 to the 3. So putting all of that together, I find the radiative correction to mh squared is of order 10 to the 19 GeV squared, or equivalently the ratio to the Higgs mass, the physical Higgs mass, is some 10 to the 15. It certainly is extreme fine tuning, where extreme is in its extreme. One can ask, well, then that's Higgs inflation. What about R squared inflation? That applies to a different regime in which alpha h can be much smaller. And indeed, what one can do is to take the parameters f0 as before, and then ask what value of alpha h do you need in order to get the correction to be of order the Higgs mass squared, so that all terms, all dimensionful terms that need to generate the physical Higgs mass are the same order of magnitude. And the answer to that is you need alpha h to be less than 10 to the minus 9, which at first sight looks a perfectly reasonable possibility. We don't have any fundamental theory of alpha h. Well, actually, we do have a slight inclination of what it should be, because the standard model by itself generates alpha h, an anomalous coupling. And here is the beta function for alpha h, given in terms of the quartic scalar coupling, the top Yukawa coupling, and the gauge couplings. And with this beta function, you can get a rough estimate of what the expected value for alpha h could be if there were no other contributions, and it would be around 0.1. So what this is then telling me, if alpha h has to be less than 10 to the minus 9, the natural value for it, or the minimum value for it from standard model contributions, plus the bare value of alpha h, has to be tuned to be 10 to the minus 9. And that would say the fine tuning of alpha h has to be done to 1 part in 10 to the 8, which still looks pretty unnatural. Okay, is that all can do? Well, I try and proceed a little bit further and ask, this was the original Starobinsky model in which you don't have scale invariance. I've been arguing for scale invariance as a starting point to discuss whether we are fine tuning. So shouldn't we consider Starobinsky model in a scale invariant version? And it's rather simple to do that. You can replace the Planck mass in Einstein-Hilbert action by a field eta squared, the Brans-Dicke field, provided the Brans-Dicke field acquires a vacuum expectation value. So the Brans-Dicke Lagrangian involves a canonical kinetic term for the Brans-Dicke field, a potential for the Brans-Dicke field, and this coupling to the Ricci scalar. These terms are all scale invariant, so you replace the scale dependent piece by a scale invariant piece, but now you want to spontaneously break it. And the spontaneous breaking of this scale symmetry, interestingly, proceeds without a potential. Something that we called inertial symmetry breaking occurs, and eta is driven to have a vacuum expectational value proportional to the Planck mass. Well, of course, the Planck mass has no particular meaning, but when we look at ratios, it will have a meaning as to what the value of this field eta is. If you're interested, I can at the end tell you how that works, but for the moment, let me just say we do have spontaneous breaking of the scale symmetry, and it generates the Planck mass as required. It also comes with some other physics, which is that we have a global symmetry which is spontaneously broken, so you will have a massless dilaton. And it's relatively easy to separate the massless dilaton from the rest. The fields have a factor of the dilaton according to their dimension. So for the scalar fields, you have e to the minus sigma, for the metric e to the 2 sigma. And in terms of the Hatted fields, you have a theory which involves the dilaton and the Hatted fields. And before the contact terms are added, the dilaton actually decouples, but picks up a coupling with the contact terms, which incidentally leaves a Z2 symmetry invariant associated with the dilaton. Now, you can just now go through the procedure that I discussed in some detail for the scale-dependent case. I work out the fine-tuning, and the structure of that fine-tuning has a different form. It involves now, in addition, this anomalous coupling of the Brans-Dicke field alpha eta, as well as alpha Higgs. The general form looks rather similar. It's not exactly the same. Oh dear. It has this factor of alpha eta, but when we studied inflation in this model, which doesn't significantly change from what I discussed before, you find that to get inflation, you want alpha eta to be small, and in fact, you can take it to be 0 with while being consistent with inflation. And this then means that instead of a factor of alpha h, you end up with effectively a factor of alpha h squared in your fine-tuning measure. Well, how does this affect fine-tuning? Well, for Higgs inflation, alpha h is determined of order 10 to the minus 3. So actually, you don't change the estimate of mh squared. It's the same as a scale-independent case. So it's what I would call completely unacceptable fine-tuning. For R-squared inflation, you've replaced alpha by alpha h squared. And when you take alpha to be small, which is what you need to suppress this, you find, of course, you can reduce the fine-tuning in the original parameter alpha h quite significantly to 1 part in 10 to the 3 or 4, which you might say is marginally acceptable on the basis of looking for a non-fine-tuned model. Okay, so let me start up with a summary and some comments about what we've been discussing. Higgs inflation, in all cases that we looked at, would seem to have an extremely severe fine-tuning. So if you consider fine-tuning to be unacceptable, then Higgs inflation in the R-squared Higgs model does not work. And to the extent that Higgs inflation sort of implies the existence of the R-squared term, the R-squared Higgs model would seem to be the minimum Higgs inflation model. R-squared inflation also seems to have a rather severe fine-tuning problem in the scale-dependent case. In the scale-independent case, it was less so, and perhaps acceptable, and it's worth exploring that some more. One thing that is rather significant in looking at the, well, I'm talking mainly about the scale-independent case, but it would also apply to the scale-dependent case, is vacuum stability. We know in the standard model that the quartic Higgs coupling gets driven, if you take the central value for the measured quartic Higgs coupling, it'll be driven to negative around 10 to the 11 GeV. Thereafter, you develop a second minimum, the non-electroweak breaking minimum with a very large vacuum expectation value that you obviously have to avoid. Now, this is particularly problematic for a theory of inflation, because during inflation, you need to protect yourself against fluctuations of order h, and the fluctuations, if they take you to the second vacuum, will lead to an unacceptable situation. And Herrera and et al. Showed some time ago that you could stabilize your potential against fluctuations with an anomalous coupling of the Higgs to the Ricci scalar. But the value that they needed for alpha h was bigger than 0.36. And if you want the scale, the scale independent case to suffer from minimal fine tuning, alpha h has to be extremely small, much smaller than this. So it will not protect you against such fluctuations. And in such a circumstance, the only conclusion you can have is that your quartic interaction does not actually cross zero. It's dependent on the top mass, and the top mass would have to be less than 170.3, is it 171.3, in order to avoid this catastrophe. And that's some 2.5 sigma away from the central value. So that's something that if the measurement of MT can be improved, would be a way of saying whether or not this model remains viable. Now we have the dilaton, and so you can ask about its production and dark radiation. In the model that I've been discussing, the reheat has been discussed extensively by Gorbunov and Panin, and the reheat is shown perturbative to Higgs and dilaton. It may be in extreme parts of parameter space you can get tachyonic reheating, as discussed by Starobinsky and his colleagues, but it requires a very high degree of fine tuning in order to get that in the R² region, which is what's of interest to us. And the reheat temperature perturbatively is around 10 to the 9 GeV. And you can use the fact that the dilaton has definite gravitational couplings to work out its abundance. So just taking the results of these authors for the dilaton abundance, what I've done here is to translate that into an effective number of neutrinos, because that is something that is measured directly, and a Goldstone mode would act as though it was some proportion of a neutrino. The proportion of a neutrino in this case would be around 0.014, and adding that to the 3 plus, if you do the calculation including thresholds correctly, the number of neutrinos on their own is slightly larger than 3. You end up with an effective number of neutrinos plus dilaton of 3.06. And that's to be compared with the measurements shown down here between 3.15, 3.24, with relatively significant errors. Now, I think it's probably unlikely that these measurements will improve sufficiently to be able to see definitively a 0.014 effective dilaton abundance, but it's certainly an interesting thing to explore. Finally, dark matter. The theory we've got at the moment, apart from dark radiation, doesn't have dark matter. There are no candidate dark matter fields. The scaleron decays and you're left with just standard model states. So you need a dark matter candidate. And Gorbunov and Panin explored the possibility you should add a scalar to be dark matter or a fermion. Now, for this, assuming gravitational production only, which is what they did, for the scalar state, the production is sufficiently rapid from scaleron decay that you have to constrain the mass of this new scalar state to be around 7 keV, which would mean it's not a candidate for cold dark matter. It could only make up a proportion of dark matter.
You have 2 minutes.
Okay. For a fermion, the mass can be as high as 10 to the 7 GeV because the gravitational production, which through the scalar is through the kinetic term. The kinetic term for the fermions conformally invariant, and the coupling has to come from the breaking of scale invariance. There's the final comment then. In red, I've said we could have a dark matter candidate if instead of a global Weyl invariance, you make it local. That would then generate a Weyl photon. The Weyl photon is typically of mass, the Planck mass, but the coupling, at least in principle, you could make sufficiently small to make it a candidate for dark matter. However, its coupling is similar to that of the scalar, and so its mass would have to be of order 7 keV and provide only hot dark matter. So by itself, the theory, even in the local version, doesn't have a dark matter candidate. So my 2 minutes are up. I would like to thank you for your attention.
Thank you very much for interesting talk. So questions, please. Yes, there is a question from the, Christoph. Christoph, please.
Hi, Graham. Can you hear me?
Microphone.
Yes, I can hear you. Hello, Christoph.
Okay. I have a question to your renormalization group equation for the mass terms.
Yeah.
I mean, they are less direct than for the dimensionless couplings. So there's an exact result that if you have no gauge bosons, the second order, the electroweak phase transition is of second order. Can you see that in your renormalization group equations? I could not see that. And I think that is a non-perturbative exact result. You cannot cross a phase transition.
So that's an interesting comment. I must admit, I haven't looked at that. Just by way of backup, I should say that we did the same calculation directly, not using a renormalization group, and got the same answer. So I'm fairly confident that the RG equations are correct, but I need to think more closely about your comment.
Thank you. There is more questions? So can I ask myself, so you say that Higgs inflation and R-square inflation, they have this problem of fine-tuning, but then you consider both of them, that's help, that solves something, or just such a simple question?
I'm not quite clear what your question is. When you say consider both of them, they're both present in the same theory. In the end, I conclude that the Higgs inflation doesn't work at all for fine-tuning points of view, and that there's a marginal region where the parameters lie in the region that you'd call R-squared inflation. But the two are intricately combined in the R-squared Higgs potential. It's only a matter of parameter space that leads you to say one is the Higgs inflation, the other is the R-squared inflation.
Thank you very much. So if there is no questions, we would thanks again.
Thank you.
So we have a coffee break, which is about 20 minutes, and then now is 17:25. So at 17:45 we will start. evening section. 7 to 45.